In this video, we'll use the inner product to define the angles between two elements. So recall what we had before. So in Rn, the Euclidean space with the dot product we've proved that if I take the dot product of two vectors, we get the length of v, the length of w, cosine theta, and so we use this to get that theta is arc cosine of the dot product, length of v, length of w. We'll use a similar definition with any inner product on any vector space. So let's say I have a vector space V with an inner product. I'm going to define the angle between any two elements of V. So it's going to be the same exact formula, except that instead of the dot product, I'm going to use this inner product. So VW, we have lengths. Alright, so that's going to be the angle. And one special case that we like and that was really important for us in Euclidean space was the case where vectors were perpendicular. So we'll say that V and W are orthogonal or perpendicular whenever, well, we mean an angle of 90, so this should be 90. And since cosine of 90 is 0, this should be 0, so the top should be 0. So VW equals 0. On this side, we'd say that V is perpendicular to W if V dot W is 0. Alright, so we'll use the same word, orthogonal or perpendicular, and we write perpendicular like this, just like we did in Rn. One problem we could have with this definition is the fact that the domain of arc cos is pretty restricted. Since cosine takes value between -1 and 1, we would need this interior here to be between -1 and 1. Otherwise, arc cosine wouldn't make sense. So definition of theta to make sense. We need this fraction that's inside arc cosine to be in the domain of arc cosine, so we need it to be between -1 and 1. Alright, so we need to prove that, and that's exactly what the Cauchy Schwarz theorem will give us. So let me state the theorem and then we'll prove it. so Cauchy Schwarz says almost exactly this, just stated slightly different. I'm going to take any two vectors, so let V and W be in any inner product space. Then I'm going to look at this top here, and I'm going to send this to the other side. So I want to say that this is less than this, but it needs to be also less than minus this, so I'm going to put bigger than minus this, so I'm going to put absolute value. So this and this are actually equivalent. That's how Cauchy Schwarz is stated, but it actually means this. So if we could prove that, we would know that our angle will always be defined. Whichever two angle we take in any inner product space, we would have that the angle makes sense. All right, so let's prove this. Alright, so let me say, this is a clever proof. It's not full of insights. It's mostly like a trick that somebody found. But let's start by doing one case. Let's say one of the elements is 0. Let's say V is 0. So if V is the 0 of the vector space, then this side, well, it's 0 times W. To show that that will be 0, let me write it as 0 times 0, W, and then I can take the 0 out, and I'll get 0. All right, the second side, well, let's compute it, but anything positive will be bigger. But in this case, I'll have length of 0, length of W. Well, length of 0 is 0 times W, so I'll get 0. So that was property 4, that that 0, 0 gives you 0. Alright, so that's the first case. So we're going to be able to assume that V is not 0. And I'm going to look at a vector that's built from both V and W. So I'm going to look at, do I want to use, I want to look at TV plus W. I need to give this a name, so let's call it U. T here is a real number. For any real number T, this will be an element of V, so I'm going to look at UU. For any value of T, this needs to be bigger or equal to 0. Well, let's compute it. I'm going to multiply it out. I'm going to get TV plus TVW plus WTV plus WW. I'm going to take the T out, so I get T squared VV. I'm going to get, V's are equal because I can switch the order, so I'm going to get 2T VW, and I'm going to get just WW. So what I end up with is a quadratic in T. A quadratic in T that's always positive or 0. So let's write it as AT squared plus BT plus C. This quadratic is always positive or 0, so this has 1 or no roots, no zeros. We know how to test for this. It's about the discriminant. So the discriminant of this polynomial, which is b squared minus 4ac, we know that that's negative or 0. Okay, but let's spell out what it is in our case. B was 2 times this, so 2 times VW minus 4A is VV, C is WW. So this needs to be negative, which means that 4VW squared is less or equal to 4. This is length of V squared, length of W squared. I can cancel the 4, and then I can apply the square root to this. Since the square root is an increasing function, I can apply it to an inequality. So what I'll get is that, well, first if I divide by 4, I get this squared is less or equal to V squared W squared. And then if I apply the square root, I'm going to get the square root of VW squared. Since I know these are positive, the square root will simply cancel with the square. Here I don't know that it's positive, that's why I need to introduce an absolute value, because the square root and the square will give you a positive version of your number, and so we get what we wanted. We get that the absolute value of the inner product is less than the 2 lengths. And let me just remind you why we cared about this. It tells us that if we take our angle like we want, like we had in Euclidean space in Rn, if we take this, this makes sense, it's defined.